Hello everyone, I'm going to present defocus map estimation and deblurring from a single dual-pixel image. Depths from defocus methods have a long history in computer vision. Most of them require multiple captures at different focus settings, which can be impractical for moving scenes. Other techniques use specialized optics to enable single-shot depth from defocus, overcoming the ambiguities inherent in this problem with a conventional camera. In this paper, we provide a simple alternative by using commercial off-the-shelf dual-pixel sensors. These sensors were introduced in commercial cameras such as DSLRs, mirrorless, and smartphones to improve autofocus, and nowadays they are becoming increasingly commonplace. Each pixel of a dual-pixel sensor is split in two parts, and thus the sensor simultaneously captures two subimages per exposure. We can think of it as a two-sample light field camera or a stereo system with a tiny baseline. To see why a dual-pixel sensor can help with depth from defocus, let's consider its image formation model in a lens-based camera. This is very similar to the model for a regular sensor, except that each half pixel is integrating light from half the main lens aperture. An in-focus scene point produces identical left and right subimages, whereas an out-of-focus point produces shifted subimages. The shift, or disparity, depends on the distance of the scene point to the in-focus plane, and can be converted to depths in a calibrated system. Note that the sum of the two subimages is the same as the image from a regular sensor. From a regular image alone, we cannot tell whether the point is in front of or behind the in-focus plane, whereas from the two subimages, we can. Our goal, then, is to use the information available in a single dual-pixel image of an unknown scene and jointly recover the scene's defocus map and all-in-focus image. Prior dual-pixel works typically consider only one of these two tasks, and they suffer from a few drawbacks. Stereo methods fail to consider depth defocus and how it varies between views. Supervised methods require large amounts of ground truth for training, or they use synthetic data, which is hard to generalize to real data. And self-supervised methods use unrealistic blur kernel models. In this paper, we propose a self-supervised method to jointly perform defocus estimation and deblurring. We start with a one-time calibration step to model the left and right blur kernels of a dual-pixel camera, which turn out to be strongly aberrated. Then, for any given input image, we optimize for a so-called multi-plane image representation. We can use this scene representation to composite the two outputs, and also render the left and right views of dual-pixel images that account for both parallax and defocus blur. To recover the scene MPI, we solve an optimization problem that takes the dual-pixel image and calibrated blur kernels as inputs, and it requires no ground truth or supervised training. Let's look at the one-time calibration first. We image a regular grid of circular disks with known radius and centers, and solve for spatially varying blur kernels. Compared to previously used parametric kernel models, our calibrated kernels realistically model optical aberrations. Next, let's look at the multi-plane image representation, or MPI for short. The MPI representation was first used for novel view synthesis. An MPI discretizes a 3D scene into frontal parallel planar layers at fixed depths. Each layer is an intensity alpha image. We can then render novel views of the scene with accurate disparity by using compositing operators from volume rendering visualization to blend together these per-layer images. In our case, we use this representation to render dual-pixel images that account for both parallax and defocus blur effects. Before compositing, we blur each layer with the calibrated blur kernels, scaled by the layer's defocus distance. We can then similarly render a defocused image. And we refer to the two outputs composited directly from the MPI as the focus map and Ioannis focus image, respectively. Let's now look at the optimization we use to recover an MPI from a dual-pixel image. We optimize the MPI so that it minimizes two losses comparing input and rendered defocused images, and regularized by three priors. I will briefly go through each term and show their effects through an ablation study. First is the data loss, which penalizes differences between rendered and input images. Second is an auxiliary data loss, which is similar to the previous data loss but applied to individual MPI layers. We use this actual loss to create additional constraints on our unknowns, which outnumber knowns by a lot. Here is an example showing its effect. When we remove the auxiliary data loss, our technique produces worse estimates of both the Ioannis focus image and the defocus map. Next are two priors that force the outputs to be piecewise smooth, except for sharp edges. Without these priors, outputs have high-frequency artifacts. Last is an entropy prior on alpha channels, which encourages scene content at each pixel to concentrate onto a single MPI layer, rather than spread across multiple layers. Removing it leads to incorrect, overly blurred defocus maps. In the optimization, we also account for image noise. We assume Gaussian noise and prove that its presence makes the optimization biased towards blur kernels of smaller sizes. We account for this by introducing a bias correction term in the optimization. Without this term, the bias towards smaller blur kernels creates artifacts in textureless areas where noise is more apparent. For example, the clock area in this scene. We test our method on a new dataset of 17 indoor and outdoor scenes we captured using a Google Pixel 4 camera. To generate ground truths, we use a commercial depth from focus software called Helicon Focus. This software computes all in-focus images and defocus maps from input focus stacks. Note that we only use the generated ground truths for comparisons and not for training. Here are some example results on defocus deblurring. Despite the large amount of defocus blur and the tiny baseline, our method recovers high-frequency details and outperforms other state-of-the-art methods. And here are example results on defocus map estimation. Compared to other techniques, ours best matches the ground truth, especially on textureless regions. Here's one more result on a scene with continuously varying depth. We also quantitatively evaluate our method on both defocus deblurring and defocus map estimation tasks. It performs the best despite being self-supervised. Finally, we test how well our method and calibrated blur kernels generalize to other devices of the same model. We use data from the DPDNet paper and run our method using the calibrated kernels from our device. Compared to their outputs, ours have fewer artifacts and more details. To summarize, we've introduced a method to jointly recover a defocus map and a now-in-focus image from a single dual-pixel capture. Our method is self-supervised and does not require a large dataset with ground truth to train on. We evaluated our method on a newly collected dataset and showed improvements over other state-of-the-art methods. All of our code, data, and results are available on the project webpage. Thank you for listening.